Let's get started. Any question? Okay. Now let's talk about today's lab. So today we will be start doing the lab 12. Okay, so we will skip lab 11. Remember, you need to do the pre-lab for lab 12. And remember, for today's pre-lab, you have two tasks. Okay, so first task, you answer some question. I think you need to find the data sheet. And for the task 2, you need to build the circuit. Okay. And I received a couple email about like you cannot find the delta in the minikit, but I think the delta should come with the minikit. So I will show you the what the delta looks like at the end of the class. Okay. Okay. So today you will have 3 tasks. Okay. Before we talk about tasks, I want to let you know something. So the delta is something looks like this in your lab kit, and there is a little black strip that indicates the polarity. Okay. So this part, this part indicates the negative side, and this part is the positive side. And the symbol for the belt on the schematic is looks like this. Okay. And always the current is is flowing from positive to negative side. Okay. And there are some properties for that. First of all, it's non-linear. So even the capacitor and inductor you have played with, it's always follow the Ohm's law. Okay, that's how you can drive the transfer function. But still, it's not a linear circuit. You can say if you plot the IV curve, it's not a straight line. And then for delta, it have the forward and the reverse bias region. What that means is when the voltage at the positive side is greater than the voltage at the negative side, that means the delta is operating in forward delta region. So that's this part of the plot, okay, the positive part. And when the voltage at the positive side is smaller than the voltage at the negative side, that means it's working at a reverse bias region. For most of the delta, when it's working at reverse bias region, it will be like a open circuit. There will be no current. And then there's a turn-on voltage for the delta. So if you check the IV curve, when the current start to increase exponentially, that's about the turn-on voltage. Okay. Also, there's the breakdown voltage. So turn-on voltage is when it's working at forward bias region. The breakdown voltage is when it's working at the reverse bias region. So when the voltage at the negative side is greater than the voltage at positive side, and when the voltage difference is very large, that will cause the breakdown of delta. And for most of the time, when the delta is breakdown, it's just broken. Okay, you cannot fix it. And those are the 3 deltas you're going to play with for today's lab. There's PN delta, linear delta, and the Schottky delta. And you can see those are the plots you will get after you finish today's lab. Okay, and the PN delta, the part number I already write down here. And the symbol looks a little bit different. And if you already read through the lab menu, you could know this. Okay, so you see you can see the linear delta, there's a reverse working region. Okay, that's the design for this. It's not the breakdown, but it's just design for this. It can working at the reverse bias region. But for these 2 delta, the PN delta and the Schottky delta, it cannot work as reverse bias region. So after you doing the experiment, you will see what's the difference for those 3 deltas. Okay. Then let's talk about today's tasks. Okay. So first of all, the task 1. Okay. The task 1 is just asking 2 questions. So remember when you do when you're writing the write-up, you don't need to write the objective and conclusion. Okay, you just answer those two questions. So the first question is asking why you need a differential op-amp across the sinks resistor. So one thing I want to let you know is this semester, you're using AD2. The AD2 can directly read the differential signal. But in previous semester, when you use the benchtop equipment, so the oscilloscope on your desk, that equipment can only read the single-ended signal. So that's like a quick tips tell you. So quick tip for answer this question. Okay, so remember you are using differential. You are using the AD2, which can read the differential signal. So you don't have to use this op-amp in today's lab. Okay. And then the question 2 is asking the expression for the amplifier. So which you can directly find the answer from the datasheet. It's basically asking the output voltage and the gain equation. So the relationship between VO and the gain. And you should find those two equations on the datasheet. Okay, that's task 1. It's pretty simple. And then the task 2. Okay, you're going to start build the circuit. So the circuit will look something like this. Okay, you have an AC signal, which will comes from maybe let's say W1. Okay, then you have a limit resistor, and then you have a resistance resistor. Okay, before you build the circuit, you actually need to calculate the value for your limit, R limit, and R sense. Okay, so you will use this equation. And there is the RS in this equation, but since you're using AD2, there is no RS. Okay, RS is just equal to 0. Okay, for this equation, the VS maximum is the maximum voltage of the voltage source. Okay, so if you check the tasks, the voltage source is from negative forward to positive forward. So the VS max is just forward. And then the ID max, so that's the current, maximum current can go through this belt. Okay, that's also given in the tasks, which is 13 milliamp. And then the last thing you need to know is the VD test. Okay, so the VD test is, you can get it from the figure 12.9 on the line menu. It should be. Okay, I think it's different, but I'm not sure. It's 12. I forgot it's 12.9 or 12.5. But there is the IV curve plot on the line menu, so you know the current. You can find the voltage. Okay, so you will use that for the VD test. So after you get those 3 values, then you can calculate the equation. Okay, so those values should be around 103 if you do the calculation. And then you know your R limit and R sense plus together should greater than this value. Okay. And in the tasks, it already tell you for the R sense, you need to pick from those 3 values. And the R limit is just help you to make sure those 2 values plus together larger than this one. Okay, so to satisfy this equation, you can pick whatever the value you want. For example, you can pick this 2 plus together is 1 k-ohm, but you don't want to do that, right? If you put those 2 resistors, the value is too large, that will limit the current too much, okay? Which means maybe your current will stop at here, which you cannot see the current voltage. So you want your pick your R limit and R sense so that those 2 plus together just satisfy this equation. Okay, you don't want these 2 values are too large. Okay, so after you get the R limit and R sense, you can build the circuit. Okay, so you can use channel 2 to measure the R sense. So 2 plus and 2 minus cause the 2 sets of sense resistor. And then you can use channel 1 to measure the voltage across the band. Okay, and don't forget to put the ground in. All right, so after you do that, you should be able to see some plot and for x and y, maybe you will say something like this. Okay, some weird plot, but you can use that to plot to get the IV curve. Okay, so you will use XY mode to get the IV curve. So the IV curve, remember the x-axis is the voltage, the y-axis is the current. So you want to make sure your x-axis is the voltage across this delta, and the y-axis is current across this delta. Okay, so how you get the current across the delta is you can use the voltage cross the arsense, divide the arsense value. So that will be the current for the delta. So you can get the IV curve, and the IV curve for each delta will be looks like those. Okay, looks like those plot. All right. So I think that's the step D. Okay, I mean the question was step D. So capture a screenshot of IV curve. Okay, and then you can export the data. Okay, I think you learn how to export the data before. So you can export the data for channel 1 and channel 2 to get the IV curve. Okay, so for this time, you don't need to export the data for time because you're not going to plot the data versus time. It's only current versus voltage. So you only need the data for channel 1 and channel 2. Okay, for question 1, step E, you want to, so first of all, you want to do this measurement with only one delta, and then you can put two delta in series. So what we will get, you will get is something like this. Okay, so this one is, so this plot is only one single delta, and this plot is two delta in series. Okay, you will find out the turn-on voltage for one delta is half of the turn-on voltage. So that's two delta in series. Okay, so this is the plot you will get for the question 1 of task 2. Okay, then question 2, you just put the you want to answer why we not put the two delta in opposite direction. And then question 3 and question 4, you are going to repeat the same thing. Okay, you repeat the same measurement. You just change the delta, and then you export the IV curve. Okay, then the question 5 is after you do all the measurements, after you get the IV curve, you need to answer what's the difference between those three deltas. Okay, you can answer the difference from their turn-on voltage. Okay, each delta have different turn-on voltage. And also, for some of the delta, they have the reverse bias region. Okay, it can't work at reverse bias region. So that's the difference you need to find out. Okay, so that's task 2. Any question about task 2? Okay. Then let's say task 3. Okay. So task 3, which you are going to build this circuit. Okay. Before you build the circuit, you actually need to draw the load law. Okay. So how you can draw the load law is, first of all, you want to find the short current and the open circuit, open voltage. What's the short current is when you short this circuit. Okay. When you have something like this, the current goes through here. That's the short current. Okay. And the open voltage is when you open this part, the voltage at this between these 2 points. That's the open voltage. Okay, so after you get those two values, okay, you can put those two values as 2 points. Okay, so the current at here is short current. The voltage at here is open voltage. You connect these two lines together, that will be your load law. Okay, so you will have the equation for your load law, and then you have that's one line you want to draw, and then you want to draw the line for your delta. Okay, which you get from your task 2. Okay, you put those two two lines in one graph, okay, then you have an intersection point. That point will be your operating point. Okay, so you can get that voltage and current um, by just draw this plot. Okay, you draw the low line and you put the every curve you get from task 2, put them in same graph, and you find the intersection point. Okay, so that's all you need to do for task 1, 2, 3. Okay, then for task 2, you need to build this circuit to verify your result. Okay, so you build this circuit according to the schematic on your tasks, and then you measure the voltage across this cell. That voltage will be very close to the value you get from the graph. Okay, I think that's all for task 3. Okay. Overall, I think today's lab is not too hard. And before I end, I want to show you the delta looks like. Okay, let me share my screen. Okay, so uh, okay, so this is I think the PN delta. So 1N4148. So your PN delta is looks something like this. Okay, and then this is 1N5248. So that's the no, not this one. Okay, this 5181. This is Schottky delta. Okay, something looks like this. But I think this one is looks close to the Zener delta you have. Okay, so those are the deltas looks like in your lab kit, and you should able to see. So this is just a picture. So you should able to see there are some parts number printed on the delta. Okay, it's very small. It looks very small, but you should see the part number. Okay, so think even you have the mini kit, you should have those parts in your lab kit. So please double check your lab kit. Okay, yeah, I think that's all for today. Any questions? Okay, if there's no question, you can start to do your experiment.